The last part of Chapter 5 deals with the kinetic molecular theory. Essentially, we've been talking a lot about what happens when gases are mixed together, but not so much why. So, the kinetic molecular theory aims at explaining the behavior of gas, and there are four different postulates that you need to be aware of. The first is that the particles of a gas are so small compared with the distances between them that the volume of the individual particles it could be negligible, zero. And what that means is, so if we were to look at a solid, you could see the particles are all packed together. There's a volume there. But if you look at a gas, the particles are spaced quite far apart. The second postulate is that gas molecules are in constant motion, and the pressure that results that that we talk about when we're talking about gases is actually a result of the collisions of the gas molecules with the chambers that they are being held by. The third is that gas molecules exert neither attractive nor repulsive forces on each other. So they're not attracting each other, they're not repelling each other. There's no forces happening between the particles themselves. The final part of the kinetic molecular theory is that the average kinetic energy of a gas is directly proportional to the temperature in Kelvin. And this is an important one, so I'll say it again. The average kinetic energy of a gas is directly proportional to the temperature of the gas in Kelvin. So let's go through some ideas to try and think about this a little more. So we have two balloons. The balloons have the same volume. One has helium, another has hydrogen. We're going to go through a series of statements, and the answer is either different or the same. First off, the pressures of the gases in the two balloons, what are they? Are they the same or are they different? If you said the same, you would be correct. If you think about it, the ideal gas law says that 1 mole of any ideal gas occupies the same volume as 1 mole of any other gas under the same conditions of temperature and pressure. So basically, PV equals nRT. If the volume's the same, then the pressure needs to be the same. Next up, the temperatures of the gas in the two balloons. They are also the same. Again, it's the same thing. If the volume's the same and the pressure's the same, then the temperature also has to be the same. The number of moles of the gas in the two balloons is also the same. Again, PV equals nRT. If one of those things is the same, and we know the problem told us that volume was the same, then the pressure has to be the same, the number of moles has to be the same, and the temperature has to be the same. The densities of the gases in the two balloons. This one is different. Density is not accounted for in the ideal gas equation, PV equals nRT. It is different. Density is mass over volume, and we know that the mass of helium and hydrogen are different. Let's take another look. Which of the following best represents the mass ratio of these two gases, of neon to argon, in the balloons? The volume of the neon balloon is going to equal twice the volume of the argon balloon. With that in mind, which of the following best represents the mass ratio of neon to argon? The correct answer here is 1 to 1. So assuming that the internal pressures of both balloons are equal, and we know that argon weighs twice as much as neon per mole, then the ratio has to be 1 to 1, because neon weighs half as much as argon, yet there's twice as much of it. Next up, we have a sample of nitrogen gas in a container fitted with a piston that maintains a pressure of 6 atm. Initially, the gas is at 45 degrees C at a volume of 6 liters. Then we cool the gas. Which best explains the final result once the gas sample has cooled? Think about it. The correct answer is that the volume of the gas is going to decrease. need to keep in mind that it said in the problem the piston maintains a constant pressure. So if the temperature is going to go down and pressure can't change, what's left? Volume. The gas sample is then cooled to a temperature of 15 degrees C. Solve for the new condition. Again, since the movable piston keeps the constant pressure overall, what condition will change? Pause it here and see if you can get 5.43 liters. The way that you would solve this is using Charles' law, and that's V1 over T1 equals V2 over T2. So the initial volume is 6 liters. Over the temperature, the problem said 45 degrees. We need to convert that to Kelvin, so we'll add 273. And that will equal the new volume, which is our X, over the new temperature, 15 degrees plus 273. That'll give us 5.43 liters. Another thing to mention here is we have this equation here for what is considered the root mean square velocity. Essentially, this is the velocity of the gas particles, but because gas particles move in all different directions, we look at the root mean square. So the root mean square velocity is going to equal the square root of 3 RT, and the R value that we use here is 8.3145. These aren't specifically something you have to memorize, although you will have to know which R to use when. In this case, we're going to use the R that incorporates joules into the unit. The temperature, so 3 times R times temperature in Kelvin over the mass of the gas. Importantly, though, the mass needs to be in kilograms. And it's in kilograms because that is how our R value units play out. The final units of root mean square problem are in meters per second. Quickly, I'm going to just say a couple of things about section 5.7, which is about effusion and diffusion. Diffusion is a term for the mixing of gases. Effusion describes the passage of a gas through a tiny hole. And the rate of effusion measures the speed in which the gas is transferred into a chamber. So we have a gas. If the gas is moving through a tiny hole, we call it effusion. And we can use Graham's law to look at how fast that happens. So the rate of effusion for gas 1 over the rate of effusion for gas 2 is going to equal the square root of the molar masses. And that is all for chapter 5.